Often we want to do exact quantitative analysis. We may want to know exactly how much the average risk premium in Rotterdam goes up next year, for instance. And if we want to do calculations, then parametric families are useful. I'll show you now a few popular parametric families for probability weighting functions. Here is a page from the book, Equation 6.4.1. This is a parametric family. It was introduced by Parametric. It's called compound invariance family. It has two parameters A and B, and it's quite easy to see that parameter B is just the power of the function. And of course, the bigger the power, the more you push down the curve, so the lower it gets, the more pessimism there is. So this is the parameter, I called it motivational on a previous meeting. This is a parameter that captures the motivational aspect of probabilistic risk attitude. It is more difficult to see what parameter A is doing. So I'll show you in graphs what parameter A is doing. Here we have 4 panels with graphs from this Parametric family. Every panel, we keep A constant and we vary B. And we see that B is doing what we could already easily see from the formula. The bigger B, the more the curve is pushed down. So B is indeed index of pessimism. The graphs confirm what we already know. Well, it was more difficult to see what A does. To understand what A does, let us keep B constant. Let us do every panel, we look at B equal 1. That's the fat curve in every panel. Then we move to the right, we see what changes if A changes. And then you see visually, if A gets smaller, more and more pronounced the inverse S shape becomes. So it looks like A is an index of insensitivity, like with insensitivity. And indeed also for other parameters of B, you can see the smaller you make A, the more insensitivity there is. So this is this cognitive component as we interpreted it. If we look at the special case here, A equal 1, then there is no insensitivity. It's in a neutrality level. It can, well, the formula is already gone, but it can be seen from the formula that then we have the power family. Then we get the power function. So the power family is a subfamily of the two-parameter Parametric family. I also have here a panel with A exceeding 1. Then we have the opposite of inverse S. Empirically, that's not so interesting, and also psychologically not plausible to happen. So A smaller than 1 is the empirically interesting case. Another family is the formula that you see here. This is called Gaussian-Einhorn family. Like Parametric, it has two parameters A and B, and although the mathematical formula looks quite different, these parameters have quite the same effect. Parameter B, it's not very difficult to see from this formula that parameter B is a parameter of elevation, but now the bigger B is, the higher the curve is. So B is an index of optimism. And again, it is more difficult to see from the formula what parameter A is doing, but I show you graphs that illustrate it. Here we have graphs again 4 panels. Again, every panel has a constant, and again in every panel you see that B indeed does what the formula already, well, maybe a bit more difficult, but still it could be seen. The bigger B, the higher the curve, the more optimism now, so the more attraction. This was the motivational component, risk aversion, risk seeking. That's what B does. A was more difficult to see. Let's again do this thing. We take one constant B, let's do B equal 1 again, and again in every panel that's a fat curve. Then we move to the right, we change A, we see what happens. And we see, as with Parametric, the smaller A, the more insensitivity we get. So these curves, indeed, and that also for other B's you can see, again, always the smaller A, the more insensitivity. So A is an anti-index of insensitivity, B is an index of optimism, the two components that we want to have that are psychologically interesting, and also empirically we find that these families fit data quite well, so they do quite what we want to do. I should say, I think in the Parametric family, if you look more closely to the figures than we did, you can see that the separation of the parameters is not very clean. This A parameter that should be insensitivity is also a bit impacting the elevation. So the separation is not so 100% clean. With Gaussian-Einhorn, it's better. And it can also be seen mathematically that in a way they are orthogonal, the two parameters. So with Gaussian-Einhorn, there's a better separation that B is really elevation, the motivational component, and A is really insensitivity, the cognitive component. Now a third family I want to show you is here. This simple family is the neo-additive family, as it is called. And of course the weighting function has to be 0 at 0. It has to be 1 at 1. But other than that, we take it just linear in the middle. And we allow for discontinuities at PS0 and PS1 with this family. It's mathematically very easy and simple, of course. It's very tractable. Maybe you think it's not very realistic empirically, but it's not so bad empirically, because the main thing happening empirically is the jumps at PS0 and PS1 at the extreme probabilities. And then whether in the middle it's a bit concave or convex or linear, that's not so very pronounced. So this family is not so bad empirically either. And it's so very tractable mathematically that it's often used, it's popular, and right so. Often when you do quantitative analysis, you want to do regression, you want to have indexes. Maybe you have a group of subjects. For every subject, you want to have one number indicating how pessimistic the subject is or optimistic. You want one number that indicates how insensitive, how much discriminatory power for probabilities that subject has. Well, these families can be used to obtain such indexes. For instance, if you have for every subject a data set or maybe the whole curve, then you can use a predict family. What you do is you take the predict function that best fits the data, and then the parameters A and B from that predict family you take as the indexes for your subject. The same you can also do with Gaussian-Einer. I think Gaussian-Einer is a bit better, but this is better indexes. And you can also do neo-additive. Now, it can be seen that although neo-additive usually fits the data not as good as the other two, because it's a bit simplistic in the middle maybe, so it's not so bad, but still. But it turns out that if you nevertheless derive the indexes from the neo-additive family, and maybe I should explain a bit about the indexes. Of course, it's quite obvious that A, the slope parameter, that is insensitivity. The smaller A, the smaller the slope in the middle, less discriminatory power, and the more this, empirically, you can interpret this as inverse as jumps at 0, 1 and shallow in the middle. So this neo-additive can be considered a special case of inverse S. Then A is an index of insensitivity, and for instance, the area under the curve can be taken as an index of elevation of optimism, and that can be seen B plus A divided by 2, or linear transformation of that. So anyway, in that manner, you can also use the neo-additive family to fit data and then get indexes. But then these indexes turn out to be quite good. They have all kind of good properties, and even if the neo-additive family is not fitting the data so well, these indexes that you derive from them, they very well capture all kind of things going on empirically and psychologically in the minds of people. So I usually quite propagate using the neo-additive family for it. Also, it's practically because neo-additive, getting the best fitting linear curve in the middle, that's with linear regression. There's many standard programs that can easily do it for you. And then best fitting only in the middle, right? Not at the extremes. So there are many advantages, pragmatic, but also more substantive to using the neo-additive family. Anyway, these are some popular families. And with this, these tools for quantitative analysis, I'm going to finish this recording.